Okay, in this video we're going to look at a couple of different ways of using the acceleration rate of change. In the examples we've done so far, we have anti-differentiated with respect to the dependent variable, and we've also anti-differentiated with respect to t, which is these first two options in the table above, which is all well and good when I know something about t, but it's possible that we can get some equations where we don't know anything about t. And in those cases, these other forms of the acceleration rate of change are really useful because it keeps the variables in the equation all in terms of x and v. So that way, when my initial conditions are in terms of x and v, I can still work with substitution and solve more of the problem. So let's work through a couple of examples. The first example is an object moves in a straight line so that the acceleration is given by a equals 1 plus v. So a equals 1 plus v. And its velocity is 1 meters per second at the origin. So the origin's a position and we've got the velocity. Find the velocity at 2 meters per second. So it wants me to find out, find the position when the velocity is 2 meters per second. All right, so what it is telling me is that I have an equation that is in terms of v, and my initial conditions are in terms of x and v. So let's actually start listing some of the information that we have here. So for example 1, we have my equation is a equals 1 plus v. I have the velocity is 1 at the origin, so that is v equals 1 when x equals 0, and we need to find x at v equals 2. So here's all of my information that I need. So I'm going to use the equation a equals v dv dx. So all that means is to solve this problem, I'm going to substitute in v dv dx instead of a. And when I do this, to solve this expression, I'm going to try and work out what x is. So to do that, the first thing I'm going to do is divide both sides by v, which gives dv dx equals 1 plus v all divided by v. And I want to find out what x is. So I can't integrate in terms of x here, so I need to flip my rate of change to write it as v over 1 plus v. And now I need to anti-differentiate this expression. So I'm going to find out x by finding the integral of v over 1 plus v dv. And I can go a little bit further here. I can substitute in my values. I know at v equals 1, x equals 0. And I want to find out the value of x at 2. Alright, so now I've got to be able to find an antiderivative of v over 1 plus v. So I could just break out my calculator and cheat here, but I'm going to do this by hand because this is an interesting question to consider for exam 1. And you need to be able to remember what technique to use to anti-differentiate this. And the way I do it is I can use partial fractions, or I can just do a long division. And the way I recognise that is the top line has degree 1, and the bottom line also has degree 1. So if the top line is of equal or greater degree than the bottom line, then we can always do division before anti-differentiating. So I'm going to do this with long division. I want to do v divided by v plus 1, which goes in there one time, and then I multiply it. So 1 times v is v, 1 times 1 is 1, put a plus 0, I subtract them, which gives me the v's cancel out, and then I get 0 minus 1 is minus 1. So this is my remainder, and I can write my expression as v over 1 plus v is exactly the same as 1 minus 1 over 1 plus v. Alright, so let's substitute that into my expression. I've got 2, 1, 1 minus 1 over 1 plus v dv plus 0. And this will find the value of x at v equals 2. Alright, now, so anti-differentiate gives me v minus log to the base e of 1 plus v, and that is between 2 and 1, and I've got a plus 0. Substitute in my values, I get 2 minus log e of 3 minus, so that's the first part. Now substitute in the 1 minus log e of 2, that's the second part, and I'm going to keep my plus 0 just to show that I knew it was there. And then simplify, 2 minus log e of 3 minus 1 plus log e of 2. I'm going to ignore the 0 now, which gives me 1, and then the log e of 3 is the minus, so that becomes plus log e of 2 over 3, and I can ignore the modular sign because they're both positive values. And this is my final answer. If I type it into the calculator to get an approximate, I get 0.595, and then it's a position, so this will be in meters. Okay, now we're going to look at example 2. The acceleration of an object travelling in a straight line is given by ax equals e to the x plus 1, and we know that x is greater than 0, and the velocity is 1 at x equals 0. So find the velocity at x equals 1. So if we go through all of our values here and we consider the table above, we have a function for acceleration in terms of f of x, and we also have values for x, and we have values for v. What we don't have is we don't have anything to do with t. So we don't want to bring t into this expression. We want to choose one of these other options to represent my equation. So let's start working through this example, and we're going to list all of our key information before I start. So example 2, and the key information I have is that acceleration is equal to e to the x plus 1, and I know that x is greater than or equal to 0. We also know that x is equal to 0 when v equals 1, so we've got an initial condition, and we want to find the value of v, so find the velocity when x equals 1. Okay, so let's start. We're going to rearrange this equation, or I'm going to substitute in a different rate of change into this equation for acceleration. So I'm going to replace acceleration with this expression, and then I'm going to anti-differentiate. Now this is actually quite easy to anti-differentiate. It looks a bit complicated, but it is as simple as when I move that dx to the other side, or I find the rate of change in terms of x, I'm left with 1 half v squared equals the integral of this. So that gives me 1 half v squared equals e to the x plus c, and I can find out the value of c when x equals 0, v equals 1. So that gives me a half times 1 squared equals e to the 0 plus c, which is 1 half equals 1 plus c equals negative 1 half. Okay, so I've got my c value. Now, just for the record, I could have used this shortcut, which is the numerical method, and using a definite integral to find c in one step. But what I do have to remember if I'm going to use this technique, I want to find out the velocity when x equals 1, and I want to find the velocity when I know that x equals 0. Sorry, I know that x equals 0, the velocity is equal to 1. But I've got to remember that my expression isn't just a v here. My expression is a half v squared. So the value that I add to the end has to be a half times v squared, which in this case is 1. So if I wanted to use a definite integral on my calculator, I would have to use this expression rather than just putting a plus 1 on the end of the equation. But I've got c now, so I'm going to set this up. I've got a half v squared equals e to the x plus x minus a half. And I want to find out what the value of v at x equals 1. So let's substitute 1 in there. Which gives me e plus a half is equal to a half e squared times everything by 2, which is 2e plus 1, and then take the square root of both sides, and I get plus or minus the square root of 2e plus 1. Now I do need to spend a little bit of time considering, can I actually have a plus or minus velocity here? Just ignore that notification at the top. Not even sure what that's about. So plus or minus velocity here. I want to now consider if we know that acceleration is given by e to the x plus 1, and my value for x is greater than 0, then that means my acceleration is always going to be greater than 0. And if my acceleration is greater than 0, I'm going to be getting faster and faster, and it's in a positive direction, so my velocity must also be greater than 0. So I need to actually write, if x is greater than 0, then v will be greater than, go back to my equation. I can work out what it's going to be exactly, but I know it's going to be greater than 0, so I can exclude the negative value and just put my answer as the square root of 2e plus 1. And that's the end of the